All right, guys, welcome to another episode of CUDA Education. Today we're going to talk about axis aligned bounding boxes, AABBs. Um, if you want to run these examples on your machine, you need tutorial number 1 that gets you the Vulkan API installed on your Windows-based machine with a Vulkan-capable GPU. If you want these examples here, all of these examples on your machine, you need to get tutorial number 15. Okay, that walks you through the process of installing all these examples on your machine. If you want the ray tracing examples, if you want the ray tracing applications to run, you need to make sure your GPU is also ray tracing capable. For NVIDIA, I know it's RTX. I can't talk about the other vendors, but for NVIDIA, if you want the ray tracing applications to run, you need an RTX or greater or later GPU. All right. We're dealing with axis aligned bounding boxes. So, as we have said previously, when we are running this example, we have a bunch of spheres that are procedurally generated. Procedurally generated means that it's mathematically generated. We're not passing in any vertices. We're not passing in any data. We're not passing any mathematical models or anything like that. This is organically generated using the equation of a circle. Okay? So we generate these spheres organically or procedurally, what they call procedural geometry. And it's a beautiful thing for computer graphics because it's not expensive. You're not managing data. You're not doing heavy processing. You're basically organically running an equation and generating a sphere. And you could get some color, add some color to it, whatever. It's not computationally expensive, and it's not memory and data and data transfer expensive, which means you could have many spheres. Ideally, in computer graphics applications, you want to make things procedurally using procedural geometry as much as possible, because it doesn't hit your frame rates, all that stuff, right? It's just a lot better. Problem is, in ray tracing application, rays can't see these procedurally generated spheres. They can't natively or inherently see these spheres. As a result, we have this thing called axis aligned bounding boxes, which is a three-dimensional square that surrounds each of these spheres. So these three-dimensional squares surround these spheres, and whatever happens, whatever the rays hit inside of those squares is recorded as a hit or an intersection, however you want to call it, right? It's recorded as an activity, as an event, as something happening. Only what happens inside of these squares is recorded, right? I don't have the history of all of this. I'm not well versed as to why all of this is the way it is. But in order for the camera system and a ray tracing application to see the spheres, you have to surround it with these axis aligned bounding boxes. In our case, it's a square, right? A three-dimensional square. So every sphere has their own axis aligned bounding box. And when the rays traverse the scene, the rays enter these axis aligned bounding boxes, and then they hit these spheres, and then that's how an event is recorded, a hit is recorded, and that's how we're able to see the spheres. Don't ask me why you need an AABS for each sphere. Another question was, why not just have one big sphere to one big square, one big AABS to just cover the whole blob of spheres, and then anything that happens inside of that blob or inside of that big AABS, you record it. Apparently, it doesn't really work that way, because you basically have to computationally iterate between all of the spheres in order to record hits, right? So it's like it's inefficient. It's you're running a for loop, I guess. I don't know, but that's not the way to do it. The way to do it is have an AABS, surround each sphere, and that manages intersections for each of that single sphere. Okay, that's the way I understand it, and I'm sticking with it. Okay, so what we're gonna do though is we are going to tinker with well, the AABS is the AABS is defined. It's a three-dimensional square, and it's defined by a min number and a max number. The min number is the lower left rear vertice for the square, and the max number is the upper right front vertice of the square. So remember, it's a three-dimensional square. So if you have these two numbers, you generally can know what the dimensions of the square is, right? Remember, a square is all sides are equal, blah, blah, blah. So you could, with these two numbers, you could know exactly what your AA axis aligned bounding box is, okay? So then we go here. And as you can see, for the spheres, we have a vector of AABSs, right? But for each sphere, we're defining a minimum. So it's the sphere center minus the radius, and a maximum, the sphere center plus a radius, okay? So this is the AABS being generated for each sphere. Now, let us do something. Let us disable the AABS. Let us disable the axis aligned bounding boxes. We're going to completely disable everything, right? When we run it, guess what happens? Well, we get a crash. All right, let's disable it by saying the min is 0. Well, actually, no. That's probably not going to work. Let's just say the min and the max is the same number, okay? Because I don't know these variables and all that stuff. I'm not sure exactly. Let's say the min and the max is the same number. So basically, we don't have an AABS, right? Because, you know, it's the same dot. It's the same point in space. So when we run it, our application is clean as a whistle. Now that makes sense because we don't have an AABS anywhere, right? The AABS is a dot. It's like a pixel, right? So if the AABS is just a dot or a pixel and rays are traversing the scene, you know, and there's these spheres, the rays aren't going to see anything because your AABS is basically a dot on the screen. So we don't see anything, all right? So we understand that inherently. When we make the min and the max the same number, we disable the AABS and we don't see anything on the screen. But notice that the application doesn't crash, which is cool, right? The application doesn't crash because obviously we're naming variables and we're using variables and all that stuff, okay? So let's go back to normal. So we put the AABS back to normal, we run our application, and then we get our spheres again, right? Because each sphere now has an AABS surrounding the sphere. So we record the hits, all that stuff, blah, blah, blah. Okay. Now let's do something a little different. So we're going to make the AABS 30% of the size of the sphere. So, I mean, this is just a rough thing, but we're basically taking the min value and we're only doing 30% of it. We're taking the max value and we're only doing 30% of it, right? So let us disable the first one, the normal AABS, and then we have our 30% AABS, all right? So you're making 30% on your money. That's a bad investment. All right? 30% money. So 30%. So what happens when we do that? When we do 30%, notice now that our application looks like squares, right? And This makes sense because basically what's happening is that the AABS, the axis aligned bounding boxes, are bifurcating the spheres. So basically you're just taking a chunk, a square chunk out of the actual sphere. So you have the square, but you're only just taking a small chunk out of the sphere. So you can't even really see that the circular nature of what you're taking a chunk out of because the chunk is so small, right? So think of having a ball in your hand and then you're just taking, you're using a square and you're like basically trying to puncture the ball with the square, right? So that's what this is. And as you can see, they are that's what we get, guys. So now let us be a little bit more generous. We're not going to do 30%. We're going to do 50%. Okay. So let's do 50% and see what happens. All right. We're at 50%. You notice anything different? All right. We still are basically at squares, but we're just in a bigger square. All right. So nothing to cry about. Let's do 70%. Okay, so now we're at 70% of the size of the sphere. Now we're starting to see a little bit more definition. So you can see where we're still taking a chunk out of, it's a square we're taking a chunk out of, but you could start to see where there's a little bit more of a circular nature around whatever we took a chunk out of, which makes sense. All right. So it's still a little bit skewed, as you can see, it's still a little bit off, but we now know that we're getting closer to the full picture of what the sphere is. If we do 85%, we're going to get a little bit more. We basically almost get a sphere, right? We're basically at, where I'm trying to get to the thing. Yeah, you basically, you have basically all of what you need, right? I mean, obviously, if we do 95%, we're basically there. Although it's not the whole picture, but um, we're getting somewhere. Um, we're getting somewhere, right? So 95%, and then of course, if you just do 99%, we're effectively at the full position, right? So we're basically at where we were before. Okay, and then of course, um, okay, all right. So let's just revert back to what we had before. And we're back to our original application where the full sphere is being generated. Obviously, these are like combined, so you get this thing, but for the most part, we get our full application. Okay, so this is the nature of axis aligned bounding boxes. Now, a thing that I would love to see happen is basically um, generating a visual representation of the axis aligned bounding boxes. Generating a visual representation of the axis aligned bounding boxes. The problem is that it's proving to be more difficult to do than I initially thought. So I want to see the spheres, but I want to see the axis aligned bounding boxes around each one. you know, can't make any promises in that respect, but that's something I'd love to love to achieve. Um, the other thing is that the I don't know if I mentioned this earlier, but basically, I asked why can't you just have one big axis aligned bounding box around the whole blob of spheres, right? Just have one big square that encompasses all of the spheres. But basically, it doesn't really work that way because the shader would have to iterate between all of the spheres or something to distinguish between each sphere, and it's just computationally not smart. So we do an axis aligned bounding box around each generated sphere. So for the number of spheres in sphere, all that stuff. That is the lesson for today. I'm at 16 minutes, so I'm happy that I made a shorter video for you guys that can't pay attention for too long. Yeah, guys, check out the tutorials again. Tutorial number 1 for installing the Vulkan API on your Windows-based machine with a Vulkan-capable GPU. Tutorial number 15 to install all of these examples on your machine. The examples you install might be slightly different from the algorithm I have here, because on GitHub, the author of these algorithms updates the scripts. So um, basically, the version that you get might be slightly different from what you see here. But either way, you will be able to run these examples and get get these running on your machine. I believe it's the best way to learn Vulkan, right? To have running applications on your machine, and then learn your way through the through the application. Also, highly recommend reading the spec. But I like starting with running code on my machine, and then we take it from there. All right, guys, I'm at almost at 18 minutes. I think I did good today. Thank you for watching. Tell your friends. Have a group of your friends. Work on this stuff together. It's time well spent. Play video games, but also learn how to make video games and make computer simulations and computer graphics and all that good stuff. Have a great day. Bye.